our 11th class on transport phenomena, TP11. With reference to the previous class, as I have shown you that differential momentum balance along the x, y and z axes that I have derived. So, till date you have three equations of motion, or this is also called the differential momentum balance. Also you have one equation of continuity. So, in total you have 4 equations. Now, referring to the differential momentum balance, if you examine those equations, then you will find that if I would like to characterize the variables and the total number involved in the momentum balance equation, then you will find that there is one pressure term, 3 velocity terms are there, and 9 stress terms are there. So, in total you have 13 variables. If anybody wishes to solve this momentum balance equation, then all these 13 variables need to be evaluated. However, you have only 4 equations with you. So, the question arises that how the rest 9 equations can be obtained in order to solve a momentum balance equation in a full-fledged manner. The subject matter of today's class is the methodology through which you will arrive at those 9 rest equations. So, in the today's class we will try to understand that how the solution of differential momentum balance, or you can say solution of momentum balance, how this can be executed. In order to arrive at the equations necessary for solving this momentum balance equation, for the generation of rest 9 equations, needed for arriving at all the associated variables of momentum balance equations. Second principle of transport phenomena, needs to be visited. So, what is the second principle of transport phenomena? The second principle of transport phenomena states, that rate of transfer of momentum from one point to the other is proportional to the momentum concentration, As an example, if one considers the momentum flux in x direction, then the rate of transfer of momentum from one point to another, that I am talking about the rate, so the time derivative is there, and we are considering the momentum in the x direction. So, del by t rho Vx, that should be proportional to the momentum concentration. Let it be question number 1, or it can be written as del by t rho Vx, that should be equal to a constant C into rho del by Vx by del by y. Now, with respect to the equation number 2, the negative sign is there, since the momentum flux will be down the gradient, that it will flow from a higher concentration to the lower one. Now, according to the Newton's second law of motion, what is the second law of motion? That is the rate of change of momentum. The rate of change of momentum equal to force. So, the rate of change of momentum equal to the force. So, in the present case, now we take the reference of this equation number 1. Now, in the present case, momentum change is going on along the x direction. Momentum change is going on along the x direction, whereas gradient is being taken in the y direction. Equation number 1 itself tells about these things, that you are considering the change of momentum, that is the time derivative of the momentum change in the x direction, because you have taken the x component of the velocity, whereas you are measuring the momentum concentration or momentum gradient in the direction of y, that you are describing the rate of change of the change in momentum with respect to y. So, the moment, whereas the gradient is being taken in the y direction, that is on xz plane. What does it mean? It means the nature of force from this equation. So, the nature of force, it implies that the nature of force is shear and represented as tau Ix. So far as this quantity is concerned, Cp is a function of type of fluid and constitutes an important kinetic property and constitutes an important kinetic property called viscosity, that is mu. So we can write the tau Ix is equal to minus mu dVx by dy. Let it be question number 3. Now, equation number 3 is a representation of the Newton's law of viscosity in one dimension. So, let us take the reference of the equation number 3 from here to arrive at the rest equations required to be there for solving momentum balance problems. So, taking this equation here, minus mu dVx by dy. Let it be question number 3. Now, this equation number 3 can be extended to 3 dimensions. Equation number 3 may be extended to 3 dimensions. So, it implies that various equations for shear stress may be obtained as the first equation is, if you consider first the normal stresses, then tau xx, it can be derived as any mechanics of solid book, either book written by S. Ramarutham or book written by Alexander Popov. Any books you can refer for the derivation of these equations. However, this is not necessary for the transport phenomena class. So, I am writing those equations directly. So, Extending this equation number 3 to 3-dimensional cases, the expression for normal stresses, let us tau xx, that is equal to minus 2 mu dvx divided by dx plus 2 mu by 3 delta vx by delta x plus delta vy by delta y plus delta vz by delta z. Let it be question number 4. Another expression, let us suppose normal stress in the y direction, tau yy, that is equal to minus 2 mu delta vy by delta y plus 2 mu by 3, same quantity, delta vx by delta x, delta vy by delta y plus delta vz by delta z, equation number 5. Similarly, normal stress along the z direction 2 mu minus 2 mu delta vz by delta z plus 2 mu by 3 delta vx by delta x plus delta vy by delta y plus delta vz by delta z. Let it be question number 6. Now expression for the sphere stresses, that is tau ix, that is equal to tau xy, and it will be given as minus mu delta vx by delta y plus delta vy by delta x. Let it be question number 7. Similarly, tau xz, that will be equal in magnitude with the tau zx is equal to minus mu delta vx by delta z plus delta vz by delta x. It will be question number 8. And another tau yz, that is equal to tau zy, that is equal to minus mu delta vy by delta z plus delta vz by delta y. Let it be question number 9. So in this manner, by taking the help of the aforesaid equations, all the stress terms in the differential momentum balance equations, along 3 mutually perpendicular Cartesian axes, Cartesian axes may be evaluated. Through the process of elimination. Now, assuming mu to be a constant, that I have already shown you while teaching this Newton's law of viscosity, that mu is dependent upon the temperature and pressure, and I have given the two equations, mu is equal to Bt raised to the power half divided by 1 plus A by T, in order to establish the variation of viscosity of liquids with respect to temperature. Here in the present case, I have assumed that assuming mu to be a constant quantity, that I am not considering here the variation of the coefficient of viscosity or the mu. So, assuming mu to be a constant, the differential momentum balance or you should write the components of momentum, along x, y, z axes can be given as for the x component, the equation is rho substantial derivative of Vx with respect to time, rho capital D Vx by dt is equal to minus dP upon dx plus rho Gx plus mu d by 2 Vx by d by x square plus d by 2 Vx by d by y square plus d by 2 Vx by d by z square plus mu by 3 d by Vx by d by x plus d by Vy by d by y plus d by Vz by d by z. Let it be equation number 10. For the y component of momentum, change accordingly, rho capital D by dVy by dt is equal to minus d by p by d by y plus rho into component of g along the y axis, rho gy plus mu d by 2 Vy by d by x square plus d by 2 Vy by d by y square plus d by 2 Vy by d by z square plus mu by 3, and same term here d by Vx by d by x plus d by Vy by d by y plus d by Vz by d by z. Let it be question number 11. And for the z component of momentum, the equation should be rho dVz by dt, that is equal to minus d by p by d by z plus rho gz plus coefficient of viscosity into d by 2 Vz by d by x square plus d by 2 Vz by d by y square plus d by 2 Vz by d by z square plus mu by 3 into same term d by Vx by d by x plus d by Vy by d by y plus d by Vz by d by z. Let it be question number 12. In equation number 10 to 12, with respect to the equation number 10 to 12, with respect to equations 10 to 12. Okay. D stands for substantial derivative. D stands for substantial derivative. Defined as, that I have told you in the previous classes, that is d by dt of a function f, that is equal to total derivative of this f plus convective derivative. So, plus Vx dy by dx of f plus Vy dy by dy of f plus Vz dy by dyz of f. This is the first conclusion which can be drawn from the foregoing discussion. And the conclusion number B, in a combined form, such equations can be represented in terms of vector calculus parameters, such as, if I am combining the equation number 10, 11 and 12 to write in a single form, then it can be represented as rho dy v vector by dt, because I into this component, j into this component and k into this component. So, in turn that can be written as, because the rho is the taking independent here. So, rho d by dt vxi plus vyj plus vzk. So, in combined form, rho d by v by substantial v by dt, that is equal to minus delta p gradient of pressure. Gradient is defined as, that is the del p. If I am writing this quantity, because so this quantity, so I dy p by dy x plus j dy p by dy y plus k dy p by dy z, in this manner that can be represented. So, the gradient of a scalar quantity, that is a vector quantity. So, this is a vector quantity minus del p plus rho into g vector, rho into gxi plus gyj plus gzk. So, rho g, this stands for this quantity, plus mu, this quantity may be written as del square v, that is equal to into Vx, Vy, dz. So, this quantity is equal to mu del square V plus vector del square V vector plus mu by 3 plus mu by 3, and this quantity this quantity, that will be equal to divergence of V vector, that is equal to the divergence of V vector. So, this is the vectorial representation of this equation. For an incompressible fluid, for which the equation of continuity is followed, that is the del dot V vector is equal to 0. This equation takes the shape rho substantial dV by dt, that is equal to minus del P plus rho g plus mu del square V vector, that is equal to 0. This equation is for a compressible fluid, for an incompressible fluid for which continuity equation is being followed. All such equations are called Navier-Stokes equations, These Navier-Stokes equations are of immense importance so far as the various metal processing techniques are concerned. In the different metal processing techniques such as centrifugal casting can be modeled if you have an idea, or if you have a better idea about this Navier-Stokes equation, because many times in the various metal processes you have to apply a force balance, you have to apply a momentum balance in order to arrive at an equation which is stand responsible for the explanation of all the event that is going on in that particular metal process technology. So, all such things can be modeled by a thorough understanding of the Navier-Stokes equations. Thank you. So, in the next class we will try to understand what are these overall balances. Till date we have discussed the differential balances. From the next class we will start the overall balances, or often called as macroscopic balances. Thank you.